Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual, right? So today is number two, part two of, two-part series. So I kind of assume that you have seen the first video. I will recall what a Tate coloring is, but only very briefly. So this is my kind of first try to have some more assumptions on what the reader knows. So I kind of, as I said, I kind of assume that you have seen the previous video, but well, it's really cool. So please bear with me, and we want to evaluate graphs. So kind of there's this whole idea, which we will see, well, in some form, in some version today, that kind of all easy properties of graphs should be encoded in a polynomial. Well, four-coloring is certainly not an easy property. If that would be an easy property, whatever easy is, then the four-color theorem wouldn't be such a prominent and very delicate theorem. But in some sense, it still works. And I would like to tell you about a polynomial that counts Tate colorings, which is, by the previous video, somehow equivalent to counting four colorings of a graph. And of course, you want whatever the count is, could be 1, 2, 3, 4, whatever. You want it to be in this range, and my counting here was really good. 1, 2, 3, 4. Let me try again. The counting could be 0, 1, 2, 3, and whatever you want as a count should be in this range, which would prove then the four-color theorem. So 0 is kind of a bad answer. So 1, 2, or 3 should be the correct answer, and we'll see what this is. But first, let's recall Tate coloring. So a web is a very simple idea and a very simple type of graph, a specific type of graph. So it's planar, like all of these, so embedded in the plane, no intersections or something. And around every vertex, you have three edges. So it's called a trivalent planar graph, not planar trivalent. So here you have three vertices, and you have one vertex, obviously, and you have three edges around that vertex. And that's a web. And we want to study those webs, and we are asking about colorings of webs. And the colorings we want are Tate colorings, and Tate colorings are colorings with three colors, such that, well, around each vertex, let me use three colors. My first color is whatever, purple. The next color is light green here, and the final color is, say, red. So around each vertex, you have all three colors present. That's a Tate coloring, and you want to count the number of Tate colorings, because essentially the Tate coloring is equivalent to four colorable by some version of going to the Klein-4 group that I explained in the previous video. For now, just accept that Tate colorings are equivalent to four colorings of maps, which is the four-color theorem. So we kind of want to count them, and there should be some way to count those colorings. And as you can see here, it gets a bit delicate, so it's not so obvious how that should work. The point is there is a polynomial which does the job, and the polynomial is defined recursively, which is a really, really cool idea. Okay, so here's a polynomial, or kind of the rules for the polynomial. So it works as follows, and I will show you an example on the next slide. But anyway, whenever you see, first we allow scalars, we allow linear combinations of graphs. And it's a bit strange, but we just allow it, okay? So I'm allowed to write such a picture like this, where all of these pictures are kind of local. So somewhere in the local neighborhood of a graph, you have one of those pictures here. So always think of them as living in a, and so on, and living in a disk. So somewhere you have those local pictures, and you can always kind of go back and forth. So instead of having a circle, you can also write the number 3. Instead of having a lollipop or a one gun, so the Greeks never liked one guns. I like one guns, so this is a one gun. So whenever you have a one gun, because you write 0. Whenever you have a bigun or a digon, whatever you want to call it, so the one with two edges, you write 2 times, well, the outgoing strand. Whenever you have a triangle, you can get rid of the triangle. Whenever you have a square, you get this linear combination. And whenever you have a pentagon, you get a more complicated relation. And that's it. So these are the relations. So for 0 guns, that's a circle. 1 guns, 2 guns, 3 guns, 4 guns, and 5 guns, there's a relation that simplifies the graph. So you pick out locally. So this is how it works. So you kind of locally look at your picture. So here's a square, for example, and you can replace this square by the 2 resolutions. One goes this way and one goes this way, and you get a linear combination of graphs. Here's another square, you can resolve it. Take this graph, you can resolve it in this way, and you can resolve it in this way, and so on. And that's just the rules for all of them. You can take any. So you can start with the pentagon. The pentagon relation is a little bit scary. Don't look at it too closely. The only thing you want to notice in the pentagon relation is a minus sign that turns up. Everything else is kind of non-negative, but here in the pentagon relation, you have a minus sign. And minus signs are horrible. I can tell you, minus signs are horrible. Believe me, my word, minus signs are horrible. We'll come back to the minus signs later. So I say it again, we allow this linear combination of webs, and essentially we want to evaluate the web step by step. There will be some complicated web, some nonsense, who knows. You pick out one face, whatever, triangle, and you get rid of the triangle, and you continue until you end up with the empty web. And you get, in this way, a number, because in each step, you just get some numbers, essentially. You just add them and multiply them, whatever you see. So this actually will terminate because in each step the web gets simpler, right? So here you get rid of the triangle and all the adjacent faces where we have no control because it's a local rule. They are now simpler than before. They have fewer number of edges. So this will terminate actually. So let me show you an example, a very simple one. So the theta web, which is kind of the following type of web, is just, so it looks like a theta. Yeah, so it has two trivalent vertices here and here. So both of them have three outgoing edges. There you go. And it's connected like a theta. And you can easily count that it has 6 colorings. 6 colorings. Here they are. There you go, 6 colorings. Perfect. But we can also just run the algorithm. So we see, for example, a diagon up here. So this is my local picture of a diagon. It contains a diagon. It's just a turned version of this one, but we take everything up to isotopy, up to turning and moving around. So you can get rid of the diagon. So if you get rid of the diagon, you reconnect this edge to this edge, and you just get the circle. Let me color the bottom part of the circle here green, and it will be the bottom part of the circle here. And the new redirection upstairs will be the new redirection here. And then you can remove the circle and so on. So the diagon gives you a 2, the circle gives you a 3, you just multiply the numbers, you get 2, you get 6, and that's exactly the number of colorings. The theta web has 6 Tate colorings, and the theta evaluation using these type of rules gives you number 6. And is it a coincidence? Obviously, that's kind of, well, you can answer that yourself. Obviously, it's not, but it's not obvious to me, but it actually works. So let's have a look at the statement, and then I indicate the proof. So we have this evaluation of web. So here's a very complicated web. There will be some way to make it simpler, and you get some number from that web, and the number you get is the number of colorings. And why is that? Well, let's have a look at the relations if you want. Let's take the diagon. The diagon just says this. Let me write it again. So the diagon would say the number of colorings on a web that has locally a diagon is twice the number of colorings of a web that has locally just a strand. And of course, the diagon has, if you fix the outside color, so let's say you fix the outside color to be blue, then the diagon has 2 choices. So my light blue is probably a bad color. So orange can go here, and let's say green can go here, or the other way around, while I have no choice on the right-hand side. So the number of colorings on the left-hand side is twice the number of colorings on the right-hand side. And you can use the same trick for all of those rules, and you will see that this actually really counts the number of Tate colorings. So each rule is locally invariant under the number of colorings. As I should say it the other way around, the number of colorings is invariant under all of these local moves. So you just do it, you evaluate your web, and you get a number. And if you can ever show this number is non-negative, positive, then for a certain type of bridgeless web, which bridgeless just means that you won't find any of those because they give 0. Oh, let's do this one, by the way. So why does this give 0? Well, let's see. So if you fix the outside coloring here to be blue, then there is simply no choice to have a 3 coloring, right? So you should get 0 colors. So that's why this evaluates to 0. Anyway, so this counts numbers. It's a polynomial. You get a polynomial or a number, and it counts the number of colorings. And it always terminates, it's always well-defined. And kind of what you need in the proof is that every web contains at least one of the small ones, a 0 gun, a circle, a 1 gun, a 2 gun, a 3 gun, or a 5 gun, so a pentagon. And indeed, it will always, is always the case. You can prove that by some Euler characteristic argument. Here you can see a 1, 2, 3, 4, 5 gun here in the middle, for example. Here's a 5 gun, here's a square, and so on. So you will always find at least one of them. And then you just run the algorithm, and it eventually will terminate in a number. And that number is the number of colorings for that web. And where does it come from? Just let me mention this. So there's a really beautiful video that I already mentioned last time, linked in the description. So the ICM talk of Kornheimer and Morfka, and they explain that this coloring polynomials, the coloring evaluation rules here, these ones, actually they come from the representation theory of the special orthogonal group. So there's some special orthogonal group going on here, and it gives you a really hands-on way to calculate color Tate colorings. And it's really simple. You just do it by hand instead of just evaluate, look at for the biggest face, for the smallest face, just whoop, whoop, do it stepwise, remove your web stepwise, collect the numbers, and you get the result. And why doesn't this prove, this is really amazing, like a back of the envelope calculation, instead of trying to do it by hand, just trying to find all colorings, which is way more complicated. But why doesn't this immediately prove the four-color theorem? Because essentially we want only the statement, but the problem is the final rule here has a negative sign. So everything else is positive, or let's say non-negative. So whatever you do, you just collapse things that you eventually get a positive number, but not if you use the Pentagon rule, because for the Pentagon rule, there might be subtraction, and you might kind of subtract your numbers again, and you end up with 0. So this is the whole point why proving the four-color theorem from this perspective is so complicated, because there is a negative sign in this rule. The negative sign is difficult, because you kind of, in every other step, you just increase the number. So now when you're wondering, when you have a web where you don't need the Pentagon rule, then you're good. But as soon as you need the Pentagon rule, you don't know, you need some extra argument to make sure that the number comes out not being 0, right? So negative signs means there could be subtraction, and you might end up with a result that is 0. So one sounds really, really simple, just one catch in this whole setup, and this ruins kind of the proof of the four-color theorem, if you want. And people tried that for a long time because it really looks so tempting. You just have a very simple algorithm, and you just need to make sure that you get a non-negative number, a positive number, and it's just a sign in the Pentagon rule, and just gets very, very complicated. And here's again another proof. So sketch of the proof why this works. So let's do the triangle, for example. The triangle just says the number of colorings here. Let's call it C, is the number of colorings here in any web where this appears as a local picture. Remember, this is just a local picture. Somewhere in the web I have a disk, and there's this local picture. And how do we see that? Well, let's say we fix the coloring at the outside. So purple and green here and red here. Then there's, of course, a unique way to extend it here, but there's also a unique way to extend it here. So the number of colorings is fixed on both sides. And that's essentially the proof. That's all you need to know. And then you're good to go and could try to prove the four-color theorem, which I think is pretty cool. So Tate colorings was invented to give a proof of the four-color theorem. But then there's a subtlety with a minus sign turning up in the Pentagon relation, which is kind of the last relation you need. You never need a hexagon relation. You never need a 7-gon relation or something. The Pentagon is the last relation you need. You have a negative sign that ruins your proof. Otherwise, the proof would be very straightforward, and everyone would be very happy, or at least I would be very happy. But turns out that the Pentagon is a party pooper and comes up with a minus sign. Anyway, I hope you enjoyed this video, and I also hope to see you next time.